Advancement in FPGA technologies has led to a context where these devices are no longer used just in a single system-on-chip scenario, but they are now used as a computational element, maybe even in the form of a programmable system on multiple chips, in a complex heterogeneous computing system. As shown in the figure, we are now working with a board, a card, that can host more than one FPGA. The overall system, at least in the figure, is composed by one host, but this is just a simplification that can be easily removed, leading us to a scenario where, on one hand, we can have multiple boards, cards, connected to one host, or on the other hand, we may have multiple hosts sharing the access to the same card or set of cards. Moreover, this multiple host, multiple cards architecture can be seen as the base node for a distributed infrastructure where multiple of these nodes can be connected together to realize the final computing infrastructure. Different companies, for different reasons, have demonstrated interest for such heterogeneous complex distributed system. Examples of these are IBM with the Power 8 architecture, or generally speaking, with what we can consider the Power 8 ecosystem, like the Coherent Accelerator Processor Interface and the Open Power Foundation. Microsoft with the Project Catapult, where FPGAs are being deployed in Microsoft's data centers, including those supporting the Azure cloud to accelerate processing and networking speeds. Amazon with Elastic Compute Cloud with F1 instances, making customizable FPGAs for hardware acceleration generally available to a wide audience of designers. Rift with the Rift One project, a big data infrastructure obtained via Xilinx FPGA accelerated architecture. Back to the IBM Power 8 processor. This architecture incorporates facilities to integrate it more easily into custom designs. It introduced the Coherent Accelerator Processor Interface port, also known as CAPI, that is layered on top of PCI Express 3.0 and which has been designed to integrate easily with external coprocessors like GPUs, ASICs, and FPGAs. Related to the Power 8 technology, the Open Power Foundation was founded in 2013 as an open technical membership organization with the goal of enabling the server vendor ecosystem to build their own customized server, networking, and storage hardware for future data center and cloud computing. As it can be found from the Open Power Foundation website, member companies are enabled to customize Power CPU processor and system platforms for optimization and innovation for their business needs. These innovations include custom systems for large or warehouse-scale data centers, workload acceleration through GPU, FPGA, or advanced input-output, platform optimization for software appliances, or advanced hardware technology exploitation. IBM is looking to offer the Power 8 chip technology and other future iteration under the Open Power initiative, but they are also making previous designs like processor specification, firmware and software available for licensing. The Coherent Accelerator Processor Interface, CAPI, has spawned an open technology group all of itself in October 2016. The Open CAPI consortium was founded by several Open Power members together with Dell, AMD, and Hewlett-Packard Enterprise. The idea behind Project Catapult was to utilize Altera, now Intel FPGA, to accelerate Bing and Azure. Instead of using potential less efficient software as the middleman, with FPGA, Microsoft engineers were allowed to implement their algorithm directly on the hardware they were using. By doing this with a programmable device, instead of using an ASIC, they were gaining advantages by the device reconfiguration. Field programmable gate arrays are the perfect technologies to adapt to runtime unexpected modification. They can be configured at a moment's notice to adapt to new advances in artificial intelligence or to respond to another type of unexpected need in a data center. As in the case of the Open Power Foundation, we can find something similar also related to the Project Catapult, the Project Catapult academic program. This program allows researchers worldwide to investigate new ways of using interconnected FPGAs as computational accelerators, a unique opportunity to access custom data center systems for high-demand research. The Project Catapult academic program is an initiative created by the collaboration between the Texas Advanced Computing Center at the University of Texas at Austin and Intel. A further example is the Amazon Elastic Compute Cloud F1. It is a compute instance with FPGA that can be programmed by Amazon customer to create custom hardware acceleration for their application. Once the FPGA design is ready, and this can be done by using an FPGA developer 64-bit Amazon machine image, the user has to register his/her design as an Amazon FPGA image, AF1, and deploy it to the F1 instance. So far, Amazon F1 instances are available in two different instance sizes that include up to 8 Xilinx Ultrascale Plus FPGA per instance, with the local 64GB DDR4 protected memory, with a dedicated PCI Express connection to the instance. One thing which is really interesting in using the F1 instances and the Amazon ecosystem is that once the Amazon FPGA image has been developed, this can be offered on the AWS Marketplace for other customers to purchase. Previously, I did also mention Rift with the Rift 1 project. It is interesting to see how Amazon has impacted the research done by others, and this is exactly the case of Rift. After the launch of the Amazon F1 instances, Rift started to work and it is now offering Rift Cloud, an accelerator for data analytics and machine learning that extends elastic stacks. As it can be read on the Amazon Web Services website, Rift Cloud sources data from Amazon Kinesis, Amazon Simple Storage Service, Amazon Elastic Block Store, and local instance storage, and use massive bitwise parallelism to drive performance. Moreover, it also supports high-level JDBC, ODBC, and REST interfaces, along with low-level C, C++, Java, and Python APIs.